Yes, welcome back. Welcome back. I'm John, an old YouTuber and PC gamer. Let's just continue this crazy project. I have to continue. I never had this all long lists. But this is the last Zilog. Then I will continue with this Mustang versus semiconductor factories. Now it's close to 2 p.m. So let's okay, that's a longer one. That's 7 pages. That will probably be more than 20 minutes, but that's fine. Just read everything. Yes, I have to spend some time to adjust this camcorder every time I record. Good. So 7 pages, but there's many pages of links and reference. I don't know how to say that in English, because I'm not English, I'm from Denmark. So let's read about this. But it's not working. I could not just select. Let's deactivate. Then activate. Then read to end of documents.
Zilog Z8000. Zilog Z8000 designer Zilog bits 16 bits introduced 1979 design SysTip register memory brinking condition register predecessors 80 successor Z80000 registers 16 bit general purpose 24-bit PC 16-bit status Zilog Z8000 M20 MB CPU.jpg Z8001 on the motherboard of an Olivetti M20 computer performance C data width 16 bits address width 23 bits physical specifications transistors 17,500 package S 48-pin DIP 8001 40-pin DIP 8002 The Z8000 Z8000 is a 16-bit microprocessor introduced by Zilog in early 1979. The architecture was designed by Bernard Puto while the logic and physical implementation was done by Masatoshi Shima, assisted by a small group of people. In contrast to most designs of the era, the Z8000 did not use microcode which allowed it to be implemented in only 17,500 transistors. The Z8000 was not Z80 compatible, although it featured many well-received design notes that made the Z80 popular. Among these was the ability for its registers to be combined and used as a single larger register, while the Z80 allowed two 8-bit registers to be used as a single 16-bit register. The Z8000 expanded this by allowing two 16-bit registers to operate as a 32-bit register, or four to operate as a 64-bit register. These combined registers were particularly useful for mathematical operations. Although it was an attractive design for its era, and saw some use in the early 1980s, it was never as popular as the Z80. It was released after the 16-bit Intel 8086, April 1978, and the same time as the less expensive Intel 8088, and only months before the Motorola 68000, September 1979, which had a 32-bit instructions A architecture and was roughly twice as fast. The Zilog Z80000 was a 32-bit follow-on design, launched in 1986. Contents: features registers, memory handling, other features, Z8000 CPU-based systems, limited success, second sources, references bibliography, further reading, features,
Yes, I have to read page by page. I think we need to the Z8000. I will do this after this one. Let's do that. I have to remember to do that.
Z8000 registers 1511312110006050403030201000. Bit position. Grouping main registers 16-bit, 32-bit, 64-bit RH0 RL0 R0 R0 RQ0 RH1 RL1 R1 RH2 RL2 R2 RR2 RH3 RL3 R3 RH4 RL4 R4 R4 RQ4 RH5 RL5 R5 RH6 RL6 R6 RR6 RH7 RL7 R8 RQ8 R9 R10 RR10 R11 R12 RR12 RQ12 R13 R14 RR14 R15 status register SSNEVM SPODA flags program counter 0 segment 00000000 program counter address. The Z8000 initially shipped in two versions. The Z8001 with a full 23-bit external address bus to allow it to access up to 8 MB of memory, and Z8002, which supported only 16-bit addressing to allow 64 KB of memory. These allowed the Z8002 to have 8 fewer pins, shipping in a smaller 40-pin DI format that made it less expensive to implement. The series was later expanded to include the Z8003 and Z8004 updated versions of the Z8001 and Z8002 respectively. These versions were designed to provide improved support for virtual memory, adding new status registers to indicate segmentation faults, test and set, and provide an abort capability. Registers. The register set consisted of 16 16-bit general-purpose registers, labeled R0 through R15. The registers can be concatenated into 8 32-bit registers, labeled RR0/R2//R14, or into 4 64-byte registers, labeled RQ0//RQ4//RQ8//RQ12. The first 8 registers can be also subdivided into 16 8-byte registers, labeled RL0 though RL7 for the lower byte and RH0 through RH7 for the upper, high, byte. Register R15 is designated as stack pointer. On the Z8001, register R14 is used to add a fixed offset to the stack pointer, and the program counter is expanded to 32 bits to include a similar offset. There was both a user mode, normal, and a supervisor mode, selected by bit 14 in the flag register. In supervisor mode, the stack registers point to the system stack and all privileged instructions are available. In ASA mode, the stack registers point to the normal stack and all privileged instructions will generate a fault. Having separate modes and stacks greatly adds to the performance of context switches between user programs and an operating system. 1. Memory handling. Die of Zilog Z8002. Like the Z80 before it, the Z8000 included a system to automatically refresh dynamic RAM. In most systems this is normally handled by the video display controller or external logic. This was implemented via a Spirit Refresh Counter (RC) register that held the currently updating page of memory. The feature is turned on by setting the most significant bit of the RC, bit 15, to 1. The following 6 bits, 14 through 9, are a rate measured in terms of every fourth clock cycle. With a standard 4 MHz clock that allows the refresh to be called every 1 to 64 microseconds. The remaining 8 bits select a row in memory to refresh. 2. The Z8000 used a segmented memory map, with a 7-bit segment number and a 16-bit offset. Both numbers were represented by pins on Z8001, meaning that it could directly address a 23-bit memory, or 8 MB. 3. Instructions could only directly access a 16-bit offset. This allowed the instruction format to be smaller. A system with direct access to a 23-bit address would need to read 3 bytes, 24 bits, from memory for every address referred to in the code, thus requiring 2 reads on a 16-bit bus. With segments, the addresses needed only a single 16-byte read, which is then added to a segment number to produce the complete address. The segment number only needed to be updated when the data crossed the 16-bit /64 KB boundaries. 4. When represented internally, addresses were all 32 bits long. This consisted of an upper 16-bit word with a adding 0 in bit 15, the 7-bit segment number, and then 8 zeros. This required more memory to store. A such 23-bit address used up 32 bits of register space, but allowed the addresses to be cleanly stored in the 16-bit registers and can be more easily pushed and popped from the stack, which occurred in 16-bit words. 5. The optional 48-pin Z8010 Memory Management Unit, MMU, expanded the memory map to 16 MB by translating the 23-bit address from the CPU to a 24-bit one. Internally, it held a list of 64 segments and an 8-bit pointer to the physical location of that segment in RAM. When the CPU attempted to access a particular segment, the Z8010 would translate that into an 8-bit address on the address bus, and then pass the 16-bit offset on unchanged. This allowed multiple programs to be spread out in physical RAM, each one given its own space to work in while believing they were accessing the entire 8 MB of RAM. The segments were of variable length, expanding up to 64 kilobytes in order to allow the entire memory to be accessed from 64 segments. If more than 64 segments were needed, multiple Z8010s could be used. 6. The Z8010 was not available at the time of launch, and was ultimately 9 months to a year late. 7. With the release of the Z8003/Z8004, the Z8015 was added to the lineup, adding paged memory support. The main difference is that the Z8015 breaks down the memory into 64 2 kilobytes blocks, whereas the Z8010 broke memory into 64 variable-sized blocks, up to 64 kilobytes each. Additionally, the Z8015 expands the segment number from 7 to 12 bits, and then using those as the most significant bits of the 23-bit overall address, overriding the upper bits of the original 16-bit offset. The advantage to this access scheme is that it is easy to read or write 2 kilobytes blocks to a hard drive, so this pattern more closely matches what will ultimately happen on a segfault. 6. Other features. One uncommon feature found on the Z8000, more commonly associated with mini-computers, was direct support for vectored interrupts. Interrupts are used by external devices to notify the processor that some condition has been met. A common use is to indicate that data from a slow process like reading a floppy disk is now available and the CPU can read the data into memory. Normally on small machines, an interrupt causes special code to run that examines various status bits and memory locations to decide what device actually called the interrupt and why. In some designs, especially those intended for real-time computing, a bit of memory is set aside as a set of pointers, or vectors, to the code handling a particular device. The devices causing the interrupt then set some state, typically via pins in the CPU, to indicate a particular interrupt number, N. When the interrupt is called, the CPU immediately jumps through NTH entry in the table, avoiding any need to decode the interrupt. This can greatly speed up the interrupt servicing by avoiding having to run additional operations, while also simplifying the interrupt handling code. In the Z8000, a new register supports vectors, the new program status area pointer. This was similar to a memory address in a register, consisting of two 16-bit values with the upper 16 bits holding the segment number. The lower 16 bits were then divided in half, the upper 8-bit containing an offset and the lower 8 bits empty. To call a particular vector, the external device presented the lower 8 bits, or 9 in some cases, on the address bus, and the complete vector address was then constructed from the three values. 8 Z8000 CPU-based systems. In the early 1980s, the Zilog Z8000 CPU was popular for desktop-sized Unix machines. These low-cost Unix systems allowed small businesses to run a true multi-user system and share resources, disk, printers, before networking was common. They usually had only RS-232 serial ports, 416, and parallel printer ports instead of built-in graphics, as was typical for servers of the time. Z8000-based computer systems included Zilog's own System 8000 series, as well as other manufacturers. January 1980, C8002 made by Onyx Systems used the Z8001, ran Unix System 3, came with C and Fortran 77 compilers, and had an available COBOL compiler as well. It had 8 serial ports, 1 QIC tape drive, a single 8 hard drive and cost $25K. The main processor offloaded the disk, tape, and serial I/O operations to a Z80 processor on a second board. 9. 1982, Olivetti M20, a non-IBM compatible PC that ran Olivetti PCOS, a derivative of COS/MOS or CP/M. 10. 1980–1986, Olivetti Linear 1 S1000, S6000, M30, M40, M50, M60, M70. These mini computers from Olivetti all ran GOS/Cosmos. 10. 1985, the cancelled Commodore 900 computer project. 1987–1989, the East German EAW, Elektroapparatwerk, produced the workstation/multi-user system P8000 based on the East German U8000 clone of the Z8000. 11. The Zilog S8000 computer came out with a version of Unix called Zeus, Zilog Enhanced Unix System. Zeus was a port of Unix version 7 and included what were referred to as the Berkeley enhancements. Zeus included a version of COBOL called RM/COBOL, Ryan McFarland COBOL. The availability of RM/COBOL allowed many commercial applications to be quickly ported to the S8000 computer, although this did not help its long-term success. The S8000 did find some success with the IRS and tax preparers in United States, who used the model for processing of electronically filed tax returns. 12. There was a Z8000 version of the Xenix operating system. 13. Namco used the Z8000 series in its Pole Position and Pole Position 2 arcade games. The machines used two Z8000 and 2S, the 64 kilobytes versions of the Z8000. The reported inclusion of the device within military designs, 14, perhaps provides an explanation for the continued survival of the Z8000 today, in the shape of the Z16C01/02 Serial Communication Controllers, SCC. Also, the standard Central Air Data Computer, SCADC, was utilizing the Z8000 and 2.15, the end of life notice from Zilog was sent in 2012. 16, limited success. While the Z8000 did see some use in the early 1980s, it was passed over for other designs.